Hello everybody, good evening. This particular episode will be seeing a live demonstration of an agricultural drone. And we are going to consider a specific part of the drone and we will try to understand like what are the kinds of loads acting on that particular system and we'll perform a virtual simulation on that particular system and try to visualize like what exactly would be the dynamics on the system. So this is an agricultural drone which is a hexahedron and the 3D model has been conducted, performed, and we have the different parts here. So these regions are the hexahedron arms and then you have the propellers and you also have a hub on the top that is going to cover the electronics, the complete system, the electronics with the specific sensors, hardwares, etc. And then beneath you will find a tank, and this is the polypropylene tank that we had designed. And this particular tank has got a capacity of 10 liters. So this can take up 10 liters of fertilizer, pesticides, or water, whatever it is, depending upon the requirement. And you also find a slot here on the tank, and this particular slot is for sliding the battery. So this agricultural drone will be uh, operating for a period of 40 minutes, which is the endurance. This will be capable of spraying about 5 acres of land, agricultural land. And now since this is a fully autonomous system, the drone has got the capability of this will take the terrain data and this also has got sensors that is quite capable of analyzing the terrain. And based on the terrain, this also has the capacity for analyzing spectral images. So all kinds of hyperspectral imaging capabilities this have, and this also can monitor the crops. So which means like based on the terrain on which this flies, I mean the flight, this particular drone flies, this is capable of capturing the images through the computer vision system which is fit into the body. So this operates on two different systems, that is radar system and the lidar system. So this has also got a night vision capability. So based on the hyperspectral imaging capabilities, this will be able to, and this will also be able to distinguish between the colors orange, yellow, green, light green, dark green, and brown. So based on these color codings, the drone will be able to access the data. It will be able to understand whether the system is, I mean, that particular land is a fertile land or it's an unfertile land, and based on which activities can also be checked. So since this being an autonomous system, it has got a self capacity based on the requirements. Complete terrain will be mapped and it will be categorized into fertile and non-fertile lands. And all those non-fertile lands will be segregated, and the fertile lands will be subjected to all the requirements like spraying, fertilizing, and the etc. And the unfertile land will be separately taken care of, and all those requirements for that particular unfertile land, the processes which needs to be performed on the unfertile land will be performed by this particular drone. And this hexahedron drone will be operated by a drone operator or a pilot. And since this being fully autonomous, there is no continuous intervention on the system. So let us take this particular fertilizer tank or the pesticide or about 10 liter of let us consider assume that this particular tank has got ammonia fertilizer, and then this is in the liquid form. Okay, and this particular drone has got its own dead loads. So the dead loads are the complete system load, the dead weight, the self weight of the drone with the legs and with the propellers, with the motors, I mean the weights, etc. And this also has got a hub, and this electronic hub has got all the electronic components. That also has got a certain. And now the complete weight of the system is assumed to be at the center of gravity, and based on that center of gravity, the complete calculation. So now let us understand like what are all the dynamics involved on the drone. So the basic dynamics of the drones are the propellers. Okay, the propellers rotate about 50,000 to 75,000 RPM. Let's assume, and each propeller is symmetric. I mean, based on the structure. Okay, the drone structure. So the drone structure has got carbon fiber body. So the arms that you see, okay, are all completely made using carbon fiber, and there are other regions, okay, which are aircraft grade aluminum. So the legs, okay, the leg mates, the mating units, the shank, okay, all these things are made using aircraft grade aluminum. Okay, now why I'm specifically mentioning this is for the simulation, we will have to consider all these parameters, the material properties, etc. Okay, and we are going to not only perform, a structural simulation. Instead, we are also going to perform a natural frequency simulation in order to identify the normal modes. And also, these normal modes are going to, take part in the dynamic response simulation. So there is going to be combined dynamics, not only because of the structural part, because of the aerodynamics also there is going to be a dynamics involved. And now the structural dynamics and the aerodynamics combined together. Okay, the simulations are going to be performed because especially in case of the slosh, we call it a slosh. The tank is filled with fertilizer, and when the drone lifts and it pitches or it rolls forward, the fluid inside the tank also is having or experiencing an inertial jerk. And now, because of this inertial jerk, there will be an imbalance in the system. Okay, so now how these imbalances are going to affect our structure. So that's going to be our primary motivation. So now here we have seen the drone. Okay, and now we will be only interested in the tank system. And now we mentioned that the tank is going to be comprising of ammonia, and it is filled inside that particular tank, not completely. Okay, because there will be some air also. The layer of air will also be inside that, because that is going to help in case of, the case of spraying, because there are nozzles attached. So these are the motors, and below the motor region there will be nozzles attached, and these nozzles are going to spray the fertilizers, okay, or the water, depending upon the requirement, okay, based on the crop, whether it's a tea estate or whether it's going to be a paddy field, or whether it's going to be a vegetable crop. Okay, so based on the type of crop, the pressure is also regulated through the nozzles. So the spray density, okay, of all these particles, it's again a particle simulation. So the spray is a very important parameter, because certain crops will be requiring only a very minimal percentage or content of droplets, water droplets. Okay, if the size of the droplet increases, okay, there will be an excess of water that is spread. So now these parameters are to be ensured. So we have pressure. Pressure is a very important parameter. So the pressure of the fluid which is kept inside, okay, that's one. And the pressure with which the fluid is pressurized, it's sprayed out. Okay, that's a again important parameter. So and apart from that, there are other external, and the other external parameters are nothing but the speed of the propeller, the rotational velocity on each arms. Okay, so which is about 50,000 RPM, let's say 25,000 to 50,000 RPM. Now that equivalent conversion, so based on which on each arm there is going to be that much rotation velocity, and apart from that there is going to be a dead load which is going to act at the center of gravity of the system, and also there will be some remote masses which will be dumped on the system. Okay, that's okay. This is the usual way the simulations are performed on any of these kind of drone or unmanned aerial vehicle systems. Okay, so now let's get into the slush simulation. So this is the tank, and this particular tank has got a inlet nozzle, and through which there is going to be fertilizer or the pesticide or water that's going to be filled. Okay, and now let's imagine that the drone is moving this direction, that is from left to right, moving this direction. So when this moves this direction, the fluid will also experience the inertial jerk on the reverse direction, the backward direction, because of which there will be a pull experienced by the drone on the opposite direction. Okay, so now uh, now we are only considering the tank. So this is the tank in which that fertilizer, the ammonia-based fertilizer or whatever it is, it's filled, and we are going to now perform a computational fluid dynamic simulation. So this is going to be a internal flow simulation. Okay, so we are bothered or we are worried about the liquid which is inside the tank, and the liquid has got a specific properties. So like how the materials and all those things, all kinds of your steel, aluminum has got the Young's modulus, Poisson's ratio, bulk density, porosity, void ratios, thermal expansions, etc., shear parameters. So like that, we also have fluid dynamic parameters. So the most important condition is to decide on what is the computational domain. So every system or every structure which is subjected to a flow simulation first needs to be checked for whether it is going to be an externally induced flow or it's going to be an internally induced flow. Say an example, an aircraft has got a external aerodynamics. So which means we assume that it's an infinitesimal boundary of air fluid. Air is considered to be a fluid, and inside that fluid is this aircraft, which is moving at about some 700 or 800 kilometers per hour. So what happens is it's like a low viscous fluid, and when it is penetrating a low viscous fluid, there is going to be an enormous amount of loadings experienced by the structure. Okay, so the one is the head-on aerodynamics, that is the airflow, and these air are going to stick exactly over the structure, creating a boundary of sheet, a sheet, a thin sheet of that particular fluid, and that is going to induce some dynamics onto the structure. So in the nose cone, there is going to be a load, and then when it swirls and goes into the gas turbine, that is the jet engine, because the jet engine has got the propellers, and the propellers are going to is going to suck in the air that is coming in front of it. Okay, and then that's going to get compressed into the second chamber and then to the third chamber, and then there is going to be a fuel injection, and from that the entire the system ignites, and there is a thrust, okay, a propulsion, and based on that propulsion, the aircraft moves forward, and then there is a lift and a drag, and based on the lift and the drag coefficient, okay, the system lifts into the air. So that's the basic aerodynamic concept. So similarly here, this particular tank, though the tank is also experiencing an external aerodynamics, okay, we are worried about the slosh effect of the fertilizer. Okay, we definitely know when the drone is moving, in the air, okay, maybe about some 300 meters or about 600 meters, okay, it is going to definitely influence, I mean, experience, huge amount of airflow. Okay, because there are about six propellers, and each propeller is rotating at about 25,000 to 50,000 RPM, let's assume. and because of that there is a lift, and this particular lift is created and the entire structure moves up. So there will definitely be turbulences created beneath that. So now the tank is also going to experience some kind of turbulence. So that's the reason the drone will start, experiencing a small rotation. Okay, and these rotations are because the air is getting trapped. There is some kind of turbulence experienced when the air is getting trapped between these kind of structures. So certainly there are external aerodynamics, but here in this particular system, we are worried about the internal aerodynamics. So here we have the computational domain. This is the most important part. Any structure which is subjected to a computational fluid dynamics, that needs to have a computational domain. Okay, so that particular domain is going to be a infinitesimal boundary. Okay, it's all assumption. See, as we know that mathematically, when we want to integrate a certain system from zero to a specific dimension, a distance, it could be length, along the length about 6 meters, so 0 to 6 meters, or along the width for 10 meters, so 0 to 10. So like that, there is a certain dimension, a measure, and that particular measure is treated as infinitesimal here. Okay, so this is like you need to have a specific computational domain, and inside that domain is going to be this particular structure accommodated. Say in finite element analysis, in the computer-aided engineering process, in the finite element analysis, each structure is broken down into well-defined regular geometries. Either it will be a triangular, or it will be rectangular or square. Okay, so based on that, the structure is divided, and there is an interpolation tab. So the sum of volume integral 0 to say x, and integral x1 to x10, and then integral again x10 to about xn. So that xten, let us keep it as an rth factor, rth term. So like how we have the rth term for any binomial distribution. Okay, so x plus a the whole raised to n. So we have nc0 x raised to n a raised to minus n. So like that, uh, like there is going to be an rth term also. So that rth term is considered as the this one general term. So nc0 x raised to n and a raised to 0. Then the next term will be x raised to n minus 1 and a raised to 1. Then x raised to n minus 2. So like that, x raised to n minus r and a raised to r. So that is going to be the rth term. So similarly here also, this particular tank, the pesticides or the fertilizer tank, is broken down into finite volumes. So here the methodology is finite volumes. There the methodology is finite elements. Okay. So this complete boundary, the computational domain, is broken into cells. Okay, and the region, the complete region, the tank region, okay, is getting embedded into that infinitesimal cells. Okay, so now here in this computational domain, we need to define which is the solid domain and which is the liquid domain, because we know that air is acting outside, and the fluid is going to be acting inside the tank. Okay, so now we have the fluid subdomain. So based on the fluid subdomain, what we do is we describe like what is going to be the fluid kept inside. So we have to give the boundary conditions. So now in the boundary conditions, we have the initial condition, and the initial condition we are going to mention that there is going to be a certain atmospheric pressure entering this particular region. So this is the nozzle, and on the nozzle is going to be atmospheric pressure. Okay, so now let's say that the boundary element in the boundary conditions, I'm going to describe what is it actually. So is there any inlet mass flow? So in this case, there is no mass flow or anything like that. The the fertilizer or the pesticide is going to be remaining static inside this particular tank. Okay, so now what we do is we see we try to give the environmental conditions. Okay, if it is 1 atmosphere, we will define on this particular region, and in the inlet region, we define what is going to be the atmospheric pressure. And then we also define like what is going to be the conditions. See here, since it is going to be a parametric, dynamic simulation, any dynamic simulation is going to be based on time dependency. There is going to be a time, and based on that particular time is how we this one decide how the system is going to behave. So here it's a internal aerodynamics, and then we also give that there is a time dependency involved in it, and this is purely a case where there is going to be inertia and the gravity involved. So we select the gravity, and we also give it a free surface. And why we give free surface is there are two different surfaces acting inside the tank. So as I told you, one is going to be the fluid, and then there is going to be air. So it's a combination. It's a mixture of air and the fertilizer. Okay, so until it has got a air and a fertilizer, there is no friction involved. Only when there is a friction, there is a possibility for a reaction or fire accident, or one layer of the fluid is going to have or experience a dynamic viscosity or due to the other fluid which is acting on the top. So here what we do is we are going to define what is the free surface. So based on the free surface, we give the dependency. We mention what is going to be the type of fluids here. So here we are going to select the two different types of fluid. One is going to be air. Air is going to be on the top of that is within the tank. There is going to be a mixture, a combination of air and ammonia. So we are going to give air and ammonia on that. We are going to define that. And after defining it, we even have to, what is the kind of, the nature of that particular loading. So what we do is we are going to give a waveform, a sinusoidal loading, depending upon time. So there is going to be a time. So when time t is equal to 0, what is going to be the the pressure inside the vehicle, inside that particular tank, or it can be force. What is the kind of force? Okay, so here we are going to describe like what are the transient parameters which is involved. Okay, now we are going to find out few parameters. So one is the average dynamic pressure. Then we have the turbulent energy also. Then we need to find out the torque and the normal forces that is going to act. Okay, so here what we do is we perform a transient, based on the transient simulation. We are going to Okay, so we are going to perform the transient simulation, and based on the transient simulation, we will understand. I mean, we'll be able to find out like what are the the capabilities. I mean, the things here. So now, have performed the simulation. So this particular simulation is done earlier, and I just wanted to show it to you. Okay, so now here you will find. Okay, so this is how that particular fuel, not the fuel, the fertilizer. This is how the ammonia is going to flow. So this is the flow pattern of ammonia. Okay, now we will see how the air portion is also getting involved. So we will find that the blue region is going to be the air. Okay, and the other region, okay, where you find this red, yellow, orange, and all these patterns, ammonia. So this particular jerk, you are able to feel. This particular jerk we are able to experience when the entire drone is lifting and it's moving. Okay, at the dynamic condition of that particular drone, when the drone is flying, that is how particular ammonia is going to slosh within the ammonia is going to slosh within the tank. Okay, so now this is nothing but the volume fraction of ammonia. So the net volume inside the tank is going to be the addendum of the volume fraction of ammonia and the volume fraction of air. So earlier we saw what is the the volume fraction. Okay, so here you will find that the volume fraction of yeah. So this is the volume fraction of ammonia. Yes. So here it is the pressure. The pressure contours, how the pressure is varying. Okay. So it is nothing but the stagnated pressure inside that particular tank. Aluminum has got sorry, not aluminum, ammonia. Ammonia has got a vapor pressure. Okay, and there is air, and air is going to compress that particular ammonia inside. But still, because of the jerk which is experienced or the inertial jerk experienced by the tank, the ammonia is going to have a or experience a waveform, and because of that there are undulations, and these undulations are what you are seeing. So this is a typical simulation, a fluid slosh simulation. Okay, and this is an internal aerodynamics. So similarly we also have an external aerodynamics performed for the propellers and for the entire dome structure. Okay, and based on which we'll be able to find out what are the lift and what are the normal forces experienced by the drone. Okay, so I think that with this you will be able to appreciate like what exactly is the simulation, the slosh simulation, and how this is performed. Okay, it's a combination of your structural dynamics and your airflow simulation. So the combination of this. So generally, we can take it as a fluid structure interaction because there is a fluid and the tank is a structure, and how the fluid and the structure are interacting. So now there is going to be the fluid is flowing inside the structure, and because of which there are going to be a lot of relatively there are going to be a lot of inertial jerk or inertial forces and the frictional forces between two or three layers of the fluids. And now because of that, how the fluid and how the system experiences, what will be the imbalance structure. Okay, so let me conclude here, and let me also show you a particular simulation which is specifically done on the complete drone. Okay, uh, because of the external load, there is going to be a projectile which is going to be fired, or which is going to be pushed out of this particular system. Okay, and now when there is going to be a system which is going to be pushed out of the entire drone system, it is nothing but it's very similar to a bullet coming out of a cannon or a gun. So now there will be a recoil, and now how that recoil of this inertial jerk is going to affect the entire drone. So this we will be seeing it in the next episode. Okay, so let me again mention that kindly subscribe these particular episodes or whatever you are seeing here in the link, so that you will be able to get access to all the other libraries that we have. And libraries, in a sense, these are all the simulations, analysis of the simulations that we have performed for every systems or the subsystems. Okay, and something like this, I wanted to perform the reason because I wanted people to visualize, because many of them are able to understand what exactly the system or the call the mechanics of the system. But then it becomes a bit difficult when they try to explore certain complex simulations like fluid structure interaction or computation fluid dynamics or thermal flow simulations, etc. Okay, so that is the main reason for me to consider this particular not example. This is one of our systems what we have designed. I'm giving you a small idea about how the subsystem simulations can happen. Okay, so In the earlier episodes, I told you, I mean, I gave you an understanding about how the complete system simulations are performed. And if the system has got about some 100, subsystems, and each subsystem has got about some 50 to 100 parts, then the entire system is going to be a very complex system. And then performing a simulation like this is going to take days together for simulations. But how we can uh, break down that particular entire system into several subsystems, and based on certain assumptions, how we will be able to perform. So here we are able to understand like how the tank is going to contribute, the fertilizer tank or the water tank or the pesticide tank is going to induce all kinds of loadings on the drone, and how it can affect the dynamics of the drone. Okay, so thank you very much. Subscribe and share this particular episode. Thank you.